So, reactive power and RMS fundamentals. I think before we can start to really understand reactive power, we have to take another look at real power. Now, we probably all remember that real power is P equals I times V, so voltage times current. And I've got a simulation on the right-hand side here. Again, this was in our software of a purely resistive or a purely real power situation. And in an AC power system, we have this sinusoidal wave. And here I have a voltage and current where my peaks line up, my zeros line up. We would say that these are all in phase. So my voltage and current are here, in phase, peaks and zeros line up. And then we look at our real power. And this is instantaneous power. So you really, to get a rational value, you need an average. But we can see that our power has a peak and a zero, a peak and a zero. It's got a frequency that's 2x our excitation frequency, but it's all positive. And I think that's the important takeaway here is that if we average this value, it's going to come out, something right around here, but we don't have any negative power swings. This is going to be in contrast to what we're going to see in a moment, because as many of us know, this voltage and this current are not always perfectly aligned. We introduce what we call a phase shift. And in my next slide here, I've introduced a 30-degree phase shift to my voltage and current. So same exact waveforms, except I've delayed voltage and time by 30 degrees. And on the bottom slide here, I just have our angle in a very static measurement. But again, as many of us probably know, motors, inductors, capacitors cause a phase shift between voltage and current. And visually here, what we see that as a delay in time between the zero cross of my current and the zero cross of my voltage. So you can think of it as a phase shift since this is a sine wave. If we went to the math, this would be sine of something plus 30. That would be my voltage, and my current would be equal sine of something. So that's the math definition. And if we look at it in time, this is a 60 hertz signal. A 30-degree shift is going to be a 1.38 millisecond delay between voltage and current in those zero crossings. So I spent a little bit of time on that, so this will become important. I think I'm pretty consistent about using 30 degrees throughout this, so get used to seeing that number. So reactive power, what is it? Where does it come from? So we took an extreme example where we took our voltage and we aligned the voltage peak with the current zero and the current peak with the voltage zero. And this is actually a 90 degrees phase shift. So we would call this perfectly out of phase. And now let's look at power. So we just take P equals IV, and we can see that we have this negative power, positive power, negative power, positive power. And if we average this out, our power averages to zero. And you can think of this as I have some regeneration, I have some active power, regeneration, active power. We have this oscillation in power. This is going to be a really common theme today. So reactive power, at the simplest definition, is power showing up at the wrong time. It's getting to the load, but it's a day late and a dollar short. It does not go towards any real work. So reactive power doesn't do anything real. It's literally an energy oscillation. And we can see that. Again, we have that negative power, positive power. We average to zero. And the important thing about reactive power, and there's several important things, but the big one is it limits how much power can be transmitted. This current is real. This current takes up space in a power line. Power lines are rated to a certain power. So if you have a lot of reactive power, you can't pass as much real power with a given current level. So something to keep in mind. Now, I have this line here. This is one of the most debated things in science, and it's funny that it actually says that in a Wikipedia article, and I've always found it my whole career to be very true. Because in this kind of pure simulated, pure sine wave example, it's very simple. But when we start adding things in the real world, like harmonics, like unbalanced systems, like PWM inverters, we really start to see that, okay, there's a lot of frequency content here, this reactive power isn't as straightforward. We have a lot more oscillations. And we're going to discover a lot of this as we go forward in this presentation. Oh, what happened to my pen? Oh, there it's back. So on this next page, I just want to summarize what we've gone through so far. So voltage and current, zeros and peaks line up, we get all real power. Our phase is 0. Phase is 90 degrees. Our voltage and our current are perfectly out of phase. Peak of voltage lines up with 0 of current. We get this oscillation where our power is canceling out and we get this oscillatory power that does no real work. And in the real world, we have a little of both. So here we have a phase angle of 50 between 90 and 0, where we have mostly real work, but we have some reactive power. So we have some of that power oscillation. And this is where our jobs all get very interesting. Down here, I have a whole lot of math. I'm not going to go through this. I don't do math very well. But a colleague of mine does math extremely well, and in a couple of weeks, he's going to be doing a presentation where he'll go through this derivation in a lot of depth. He's an elegant speaker. I'll pitch that a little more at the end, but little preview. If you want the math, it'll be available in the future. I'm the picture guy. So now that we've described power, reactive power, voltage, and current, we've got these AC waves. They've got a frequency. They've got this phase difference. They have harmonics. They have amplitude. We can see that very quickly this becomes difficult to describe these things. And if we take that a step further, and I've already mentioned measuring power as an average, well, why don't we just average voltage and current? Well, if we take an average of a sine wave, our mean or our average comes out to 0. So that's not very helpful for us. However, we have this fun piece of mathematics called RMS, or the root mean square, where if we take, all the points under the sine wave, and we take every point, we square it, we average it, and then we take the square root of that average, or a root mean square, we end up with this constant value, and we get a value for both the positive and the negative. And what RMS ends up being in a sine wave is the DC equivalent of an AC wave. And this is pretty cool because this gives us a standard method to compare the amount of power that an AC waveform or DC waveform contains. Or for that matter, it gives us a way to describe the amount of power that a high harmonic wave and a low harmonic wave have. So we got a lot going on here. One issue with RMS, and it's not really an issue, it gives us a way of describing some extra physics, is that it's phase agnostic. DC does not have a phase. If you think about it, we're doing this RMS calculation on a voltage and on a current. And you might say to yourself, well, P equals IV, right? Well, we're taking this DC equivalent power. Good question. So this introduces us to our concept of kind of the power triangle. So real power, this is the one we're all familiar with. This is heat. This is rotation at the wheels. This is torque. This is speed. Produces work, measured in watts. And power is the average of voltage times current over a time period. Simple enough. Now, we just spent some time talking about RMS power. And I called RMS is the DC equivalent. So what happens if I take IRMS times VRMS? Well, we get that DC equivalent. So S is my apparent power number, or my apparent power variable, is VRMS times IRMS. We measured in volt amps, a very clever engineering name, and it's how much power there appears to be in a circuit. But we do need to consider that this does not have a phase angle in it. And I spent a decent amount of time talking about phase angle as well. Here's where reactive power comes up. We remember reactive power is that oscillating power. It's measured in volt amps reactive, another very clever engineering name. And we have a couple calculations here. So we have Q. Q's our reactive power, is the square root of S squared minus P squared. But it also equals V times I times the sine of theta. Theta being that phase angle between the peaks of our voltage and current. And if I take these values and I come over here, we have this apparent power, which is our DC equivalent, but that's not all going towards work. We have a real power that's all going towards work. And then we have a reactive power, which is a 90-degree difference from our real power. And we end up with this power triangle. And in the ideal world, our power factor angle is that phase shift. But as we all know, we live in the real world, so this isn't exactly true. But in theoretical, at the fundamental level, it absolutely is. All right, you're all experts on the basics. Now we get into the fun stuff where